So this application, the surface area thing, is really, really related to arc length. So what we're going to do here is we're going to take a curve from A to B, and we're going to spin it around an axis. We'll just start with the x-axis.
Wait, isn't this just the...
We're not finding volumes now.
I know, it's just the disk, but with the length instead of function.
Kind of, yeah. We're awfully close, okay? So what you're going to do now is you're going to find the area, the surface area of the thing you get when you rotate. Now, the one thing that threw me for a loop a little bit on this is they mean the surface area of, like, just the line, not if you had a solid that had ends on it. Do you know what I mean? So they're looking at just like, you know, my coffee mug, but just the major part of it, not the sides of it, okay? So, and like anything else, you start by taking these and chunking them into little pieces, right? And if you look at little like straight line chunks, what you're going to get are kind of like parts of a truncated cone. Do you see what I mean? Do you know what I mean by a truncated cone? Like no top, right? And so it turns out that what you can think about is that, okay, what matters is how far away that piece is, right? That matters. What else matters? How long it is. And so the surface area is going to be equal to, or I'll say about equal. Sorry. No, and now I can't erase it. Give me a second. Okay, now it's gone.
It's technically still there, you just can't see it.
I whited it out, yes. Okay, so let's find the length of just one piece. Or actually in that case is the... Oh, that's terrible! Oh, I know. You should try to come teach. It's really stressful.
I've done that so many times.
You've done it? Yeah. It's so annoying.
Really.
Okay, so we have our little chunk. Let's find the surface area of that little chunk. Okay.
Where did it go ginormous?
Shush, okay? So, doesn't matter. So the surface area of that little chunk, what matters is, you can think about it kind of like a cylinder. So it's pi r squared times how tall the thing is, right? Not pi r squared, 2 pi r times the length. Is that idea? This is the circumference times how tall. Does that make sense? Okay, and then in this case, so 2 pi, let's just leave that as radius for now. And for the length, didn't we do that in the previous stuff? We found the length and we said, oh, that was this 1 plus f prime of x sub I squared thing. And then times this whole delta x business that came out. Like that's what came out of the whole length thing, right?
Are we integrating all of that? Or
Yeah, so that's just one little chunk. This is one little piece. So to get the whole surface area, you add up all said pieces, right?
yeah, but
and
are
then
we
take a limit.
integrating R with that, or is R multiplied?
R is multiplying by that, and R is changing. Like the R right here is lower than the R will be way out there. Does that make sense?
So what R be at?
In this case, what would R be?
Y.
R would be Y, which in this case is f of x, right?
Yeah.
So 2 pi f of x root 1 plus f prime of x sub I squared delta x. So for about the x-axis, the surface area is equal to an integral from A to B. I'm going to write this two ways. 2 pi y root 1 plus f prime of x squared dx, or A to B 2 pi f of x.
Why don't you pull it to 2 pi?
Which you can totally do that. There's no reason I didn't. I was just happened. Is that all right?
Can you use this to derive the formula for the surface area of a sphere?
Yes, definitely. What would change if we did y-axis? You could go from C to D, say, right? And now your distance out is gonna be
Okay.
x. And this could become root 1 plus f prime of y squared dy. Or it could be the integral from, oh, and I forgot my 2 pi, sorry. C to D, 2 pi f of y root 1 plus f prime of y squared dy. And so did you guys understand how those formulas are, they're quite related to arc length, aren't they? Because they both have this expression in them, right? Okay, and I think the best way to think about it is this is kind of like your circumference, right? Because that's how far away a piece is, 2 pi r, the f of y and f of x are like your radii, right? And circumference times like the length of a chunk. That's what this is kind of doing. Now it turns out it's a little bit, your book does something that's a little bit interesting. So, and this is a really, really useful way to abbreviate this, and sometimes it's useful to not use y's for rotation about the y-axis. You don't have to, unlike when you do the disk method and stuff like this. So your book says that for the y-axis, no, I'll start with x. I'm going to go back to my big eraser. I'm going to not, my big white out pen, I'm going to not do that twice now. Okay. So for the x-axis, the formula that they give is this. They say surface area is equal to an integral from, they put no bounds on it. They say 2 pi x ds. And then for the y-axis, they say this is equal to SA is equal to integral 2, did I do that backwards? Crap. What should that say? Not x.
Should say y.
Should say y. What should the y-axis say? X. Okay. And then,
Is that how you?
and let me finish first, okay? Because then you think about, so the reason it's y for the x-axis is y is how far away it's your radius, right? And for the y-axis, x is the radius. The question is, what the heck is this ds thing that they're talking about, right? That's one. So the ds thing, they say ds is equal to either 1 plus f prime of x squared dx, or it's equal to root 1 plus f prime of y squared dy. We found that thing by kind of dividing by, I think it was, in this case, must have been dy, and factoring something out and using a derivative, right? Back on the first day we did arc length. And so you could have done that either way. And so what this thing will let you do is if you want to do y-axis rotation, you could also do 2 pi x root 1 plus f prime of x squared dx. You don't have to use y's. Because you can think x is still how far away you are, right? And the length of the curve you can find either like side to side this way or the other way. It'd be the same thing. So the point is for y-axis you do not have to use y's, and in many cases it's easier not to. And for the x-axis, do you necessarily have to use x's? What could you use instead? 2 pi y, and then the expression that would come next would be
In terms of y.
in terms of y.
That way you're not got two variables.
Exactly. And then the reason they left the bounds off of these is because if you use y's, the bound should be y's, right? If you use x's, the bound should be x's. Okay? Yeah.
The question I was gonna ask before you went into that is ds just an easy way to not have to write root whatever?
ds is what they define as an abbreviation for this expression that stands for length of curve. And I think the reason they use s is because that s of x function, we talked about curve length just in the previous example, they often call curve length s of x. Just a common use of s.
Those integrals need to be bounded on something?
They would. So like the first one, they left the bounds off because it wasn't clear if you were going to use x's or y's yet. So once you know what variable you're using, then you put bounds on.
Okay.
So let's set a couple up, because in this one, really the kicker is setting them up. So my point with that is that don't solve for y unless you have to. You know what I mean? See what I mean? Like if you want to do rotation with the y-axis, don't solve for y. Okay, so for x-axis, the surface area is integral 2 pi y ds. The picture helps me think, okay, that's the radius. And if your equation already has x's, like it's already y equals f of x, use x's. You see what I'm saying?
Mm-hmm.
Okay. Did I not give you an interval? On 0 to 1. 0, 1. Oops. Shouldn't put those yet, but anyhow. Okay, so integral 0 to 1, 2 pi y root 1 plus f prime of x squared. I think we already did y prime for this one, didn't we? On the previous problem. Negative 2x e to the negative x squared. That was the same one from the Simpsons rule problem, right? Okay, and if you're going to use x's, what has to go in for y?
Negative x squared.
What has to go in for y is e to the negative x squared. And then we'll have 1 plus 4x squared e to the negative 2x squared. You can think about this, e to the x squared as your radius, is how far away your piece is, and the other part's how long it is. And actually that e to the negative x squared curve looks something like, it's actually how you get a bell-shaped curve in stats. You do some more scaling, but, so that's rotation about from 0 to 1, about this axis. Okay, so for the y-axis, the really general formula is integral 2 pi x ds. And your choice is that you can use whatever you want for the ds. You can use the thing that involves y's, or you can use the thing that involves x's. But if you use the thing that involves y's, you've got to solve your equation for x. Do you want to do that? I don't think so. So what you'll decide here is you'll say, well, I'm going to go integral 0 to 1. 2 pi x root 1 plus f prime of x squared dx. And you say, well, okay, well, x is, how far away that piece is, and then the root thing tells me how long it is. Yeah?
So you can use whatever one.
You can use whatever one you want. Yep. So my point is don't switch unless you absolutely have to. Does that make sense? So 2 pi integral 0 to 1 x root 1 plus 4x squared e to the negative 2x squared.
And when would you absolutely have to?
You never do, really. I mean, right? So you don't. That's kind of the point, is you don't actually have to ever do it the other way.
Are you gonna ask us to do something like that on the test?
I might ask you to do it I'll probably give you a problem and say do it both ways, and maybe I'll make it really hard to solve for y. So if you try it that way, it's going to be a big pain in the butt. Does that make sense? This is the one time you don't actually have to solve for y to do rotation around an opposite axis. So, yeah, let's pick out the best one to do. Let's do number 3. Okay? Because once you have this, it's just a formula. That's this one. The curve 1 minus x squared between x equals 0 and x equals 1 spun about the y-axis. Find the result of the area of the resulting surface. So what does 1 minus x squared look like?
X at 0, 1. That's a downward parabola.
Yep, exactly. So we're taking this part of it, and we're spinning it about this axis. Okay. So for here, we're gonna use 2 pi, and then the radius is x or y? X, right, because that's your axis of rotation is the y-axis, and the radius is how far over to your thing, right? It is definitely the opposite variable. Now, because your equation has x's in it, what do you want to use for ds, probably? The x one, yep. 1 plus f prime of x dx. And if that's the case, can you put your bounds on? What are they going to be? 0 to 1. And then what is f prime of x? Negative 2x. So I have 2 pi integral 0 to 1 x root 1 plus 4x squared. Okay, and from that, can you solve it? What would you do? Pull up
You already did.
I did that. But how about the x times root 1 plus 4x squared? Don't do a trig sub. Okay, there's an easy way. Do a u sub. U equals 1 plus 4x squared. Du is 8x dx. So we've got 2 pi over 8. What did the bounds change to?
1 plus 4 is 5.
Do you guys read 1 to 5? And what does the stuff inside the integral become? U to the power of 1/2. Okay, 2 pi over 8 reduces to, so antiderivative of u to the 1/2 is u to the, times 2/3, 1 to 5, so is that a pi over 6? 5 to the 3/2 minus 1. I mean, right? Okay.
So is there a reason you always start with the 2 pi in the integral?
No, no, there's no reason. It can always come out.
So you can just start with the 2 pi outside of the
Yes.
integral and the
Yes.
answers will never change.
How about you try to set up example 4? Because in example 4, just once you set it up, and we'll do that and we'll go. So set it up and just set up the thing that finds the area of that surface. The difference is this rotation about the x-axis, not the y. I still get 3 minutes of your life. Today. Yeah. Okay. So it ends up being, so what's the reason to not try to like change to y's?
Because this will work out really well anyways.
It's more work, right? You already have x's and you have the x bounds, right? So just leave it as x's.
Plus that
If-
versus something doesn't.
Yeah, you could use like arc cosine of y, probably,
No,
but,
1 plus sine squared x.
no. That's why yeah, 1 minus sine squared converts to something. I thought that maybe,
Minus because you started with cosine and that's.
you square it, the negative goes away. I know, right, that's why I changed it to set up, don't solve, because I think to do that, you might have to like do a trig sub or something crazy like that. Yeah,
Except for a trig function.
say that again?
Trig sum for a trig function.
Why is it 2 pi, as in why is it y? Because when you spin about the x-axis, if you think about circumference times how long, the circumference is 2 pi r, and the y value is how far away your piece is. Does that make sense? If you go this way, it's x if it's spinning about the y-axis. So the previous problem, Mary Kate, was about the y-axis. Come up here.